Theorems 3 and 4 are used when you are asked to compute the probability that one event out of two or more events will happen. So this is in the form of asking for the probability of event A or event B. So first, we need to introduce the concept of mutually exclusive. So two events are mutually exclusive if the occurrence of one event makes the other event impossible. So one thing to test whether two events are mutually exclusive or not is to see if the two events has overlapped outcomes. So each event is a collection of outcomes, is a subset of our sample space. And therefore, if two events have an overlapped outcome, that means they are not mutually exclusive. Otherwise, they are mutually exclusive. So, for example, if I toss a coin and my sample space is head and tail, so event A is that a head is obtained, and event B is that a tail is obtained. So I can tell that if event A occurs, if I obtain a head, then event B is impossible to occur. So I will not definitely have a tail, right? And another example is that I roll a dice. My sample space is the 6 spots, 1, 2, 3, 4, 5, 6. And the event A is to obtain an even number. So the sample space, so the event A is a collection of my outcomes 2, 4, and 6. And event B is that 3 is obtained. So B just contains one outcome, the 3. And we can tell that if I got an even number, if I roll my dice and then I obtain an even number, then 3 is definitely not obtained, right? So one thing to test is that you can see the outcomes that make event A true is different from the outcome that will make B true. So there's no overlap for the outcomes for event A and event B. So theorem 3 says that if A and B are two mutually exclusive events, then the probability that either event A or event B will occur is the sum of their respective probabilities. This is because A and B has no overlap in the outcome, so if either A or B occurs, then you can just use the sum of their respective probabilities. Here is our textbook example. So we have a total of 261 parts that are going to be inspected, and we know that these parts are from 3 suppliers. So out of these 261 parts, 53 of them are from supplier X, and 131 of my parts are from supplier Y, and then the rest, 77 parts, are from the supplier Z. So for each supplier, they have some number of conforming parts and also some number of non-conforming parts. So I use the single color dots to denote the non-conforming parts. As you can see, they have more number of conforming parts than the non-conforming parts from each supplier. And therefore, my sample space is all these 261 parts, because if I randomly pick one part from this sample, then I can pick any one of these 261. So this is my sample space. This is the set of all the possible outcomes. So now I ask that if I randomly select a part, I wanted to find the probability that the part is produced either by X or by Z. So the event A is that apart from X, and the event B is that apart from Z. And we can tell that these are two mutually exclusive events because they have no overlap in their outcomes. And therefore, we can just use the sum of the respective probabilities. So the Px, the probability that a part is from X, is the total number of the parts from supplier X, that's 53, divided by the size of my sample space, 261. And similarly, the probability for a part from Z is the total number of parts from supplier Z divided by the sample space size, 261. And then the sum of these two probabilities is 0.498. So this gives us the probability that the part is produced either by X or by Z. The second example is that the part is either non-conforming from X or conforming from Z. So now there are still two mutually exclusive events, right? Because if event A occurs, if this part is from X and non-conforming, then this part will definitely not from Z, right? Either conforming or non-conforming, it will not be from Z. So I use NC to stand for the non-conforming and CO to stand for conforming. So here are two events, the non-conforming parts from X or conforming parts from Z. So I can, because they are mutually exclusive, I can use their respective probabilities and sum up them together. So the non-conforming parts from X is this number, right? We have 3 parts that are non-conforming and from X. So it's 3 divided by the size of our sample space, right? And then for the conforming parts from Z, we have 75 conforming parts from Z. And then we use this number. So this number is the number of outcomes that make event B true, make this event true, right? So I use 75 divided by my sample space size, 261. And this gives me the probability of conforming parts from Z. So now you sum up these two probabilities, and this gives you the final answer. The third question asks that if the part is from Z, or non-conforming from X, or conforming from Y. So here are 3 events, right? From Z, non-conforming from X, or conforming from Y, and we can tell that they are mutually exclusive. So these 3 events, whenever there's one event occurs, then I can tell that the other 2 events will not occur. So I can just sum up their respective probabilities. And you can work out this problem similarly to the second one.